Welcome to the WISE sampling distribution tutorial. I'm Dale Berger, Professor of Psychology at Claremont Graduate University. This video focuses on a key concept in inferential statistics, the sampling distribution of the mean. You can find a self-paced tutorial on the WISE website at wise.cgu.edu. I will use an interactive applet from that tutorial in this demonstration. It's helpful if you have already learned about the normal distribution, populations, and samples. You can find information on these topics and many others on the WISE site. When we use sample data to estimate an unknown mean for a population, a fundamental question is, how accurate is this sample mean? In this lesson, we will use this interactive applet to explore the role of sample size and the hidden distribution of possible sample means. We will also see how to compute the likely error that is associated with a sample mean. Suppose we've developed a new scale for life satisfaction. People who get very low scores on this scale are unhappy with their life, while people who have high scores are relatively happy. Suppose that in our state the average is 500 and the standard deviation is 100. We could use this scale to estimate the average life satisfaction for a large group by taking a random sample from that group and calculating the mean. But a basic question would be, how accurate is this mean? So that's the key question that we will address in this lesson. We can begin by considering how well we could estimate the population mean with a single score. If we have a normal distribution with a mean of 500 and standard deviation of 100, we could use our knowledge of the normal distribution to estimate the range within which scores are likely to fall and how close they are likely to be to the actual population mean. If we call our observed score x, we can convert the x scores to standardized z-scores with a familiar formula. The z-score is equal to the difference between the x-score and the population mean divided by the standard deviation. So the z-score is exactly the number of standard deviations above or below the mean that an observed score falls. So for example, 700 is 200 points above the mean, and the standard deviation is 100, so the z-score corresponding to 700 is 2. Similarly, 300 falls 200 below the mean, and the z-score is a negative 2. We could find what the limits are that identify where the middle 95% of the observations are by going to a z-table or use a computer program to find the z-score that cuts off the middle 95% of the distribution. The WISE P to Z converter is one way to do this. You can find on the website. We could interpret this to mean that with z-scores, it's likely that an observation will have a z-score within 1.96 of the population mean. We could convert this to find the middle range for scores on the x distribution. To find the x-scores that cut off the middle 95% of the distribution, we can use this z-score and multiply it by the standard deviation. So the z is about 2, so the z-score of 2 corresponds to an x-score of 700 in our example. Or a little more accurately, 1.96 times 100 gives us 196. So we could call that the likely error. That is, 95% of the scores will be within 196 of the population mean. This tells us that the middle 95% of the scores are between 304 and 696. So if we have a single observation from this population, we really don't have very much accuracy. This may not be an adequate measure of the population mean. Our score is our best estimate of the population mean, but it's give or take 196. We could improve the accuracy by selecting a larger sample size, say a sample size of 100. Now I'm going to use the applet to illustrate this. Okay, here is the WISE sampling distribution of the mean applet. You can download this applet and play along with me as we go through the rest of this exercise. We have a choice here of several different populations. We'll just use the default, which has a mean of 500 and a standard deviation of 100 and has a normal shape. And we'll also take the default of 100 cases as the sample size. For now, let's uncheck the box that says show the sampling distribution of the mean. We will look at that in much more detail shortly. But what we see now is an illustration of the population distribution with the mean of 500, standard deviation of 100. We can simulate drawing a sample of 100 cases by simply pressing this button, Draw a Sample. Now we see a histogram showing little rectangles illustrating the distribution of individual scores, 100 scores, and they range roughly from 300 to 700, a little beyond, but the bulk are in the middle. The red arrow shows the sample mean. We happen to hit the sample mean exactly with this sample. That's somewhat unusual, because if we had done this, someone else had done the study, just by luck, they will get a different sample. And let's see what we could have gotten. We could have gotten a sample mean of 502. Or on another day, we could have had a sample mean of 501. Or here's one 514. There are many different possible sample means that we could have observed just by chance. Any one sample mean that we have is actually one of many possibilities out of an underlying distribution. We can look at these observed means that we have just sampled and see that they are beginning to show us the shape of a distribution. I'll click on a few more of these and we see a little distribution emerge. But to shortcut this process, we could draw 100 samples at a time and see 100 different possibilities that we could have gotten. Click that and we see there's a very nice underlying distribution. If we did this several thousand times, that distribution would smooth out and it would look like the actual underlying sampling distribution of the mean. And it's a normal distribution which is centered right on the population mean. Now, an important point, the relationship between the population distribution and the sampling distribution of possible means is described fully by the central limit theorem. After you complete this lesson, you might try the WISE lesson on the central limit theorem. According to the central limit theorem, if the population distribution is normal, the sampling distribution of the mean is also normal, and the means are the same. However, the standard deviation of the sampling distribution of means is smaller than the standard deviation in the population, and the relationship is the standard deviation of the population divided by the square root of the sample size. In our example, the standard deviation is 100. The square root of 100 is 10. 100 divided by 10 is 10. The standard deviation or standard error of the sampling distribution is 10, while the standard deviation in the original population was 100. So the distribution of means is much more tightly clustered, especially when we have a large sample. This relationship is captured with a very elegant formula. The sigma with the subscript x bar is the standard deviation of the distribution of means. It's equal to the population standard deviation divided by the square root of n. To find the likely error for a sample mean based on 100 observations, we could find the middle range of the sampling distribution of the mean, the part that cuts off the middle 95%. A z-score on this distribution would be 1.96. The standard deviation is 10, so we would take 1.96 times 10 and get 19.6 as the likely error. That is, 95% of the sample means would be within 19.6 of the population mean. So that might be reasonable accuracy. We might be quite comfortable in knowing that if we take a sample of 100 scores, there's a 95% likelihood that our sample mean is within about 20 of the actual population mean. Now we might ask what would happen if we had a somewhat smaller sample. Let's go back to our applet and change to a sample of only 25. With a sample of 25, if we draw a sample, we see again the scores in the sample reflect the distribution in the population, with the mean relatively close to 500. We draw another sample and we find a similar sort of result. That is, the samples all look like they all come from this population, but the sample means hover around 500. Let's take a look at that distribution, and we might notice it's spread out a little more. If we do 100 of these, it's more obvious that the sample means are spread out more than they were when the sample was size 100. We can look at the sampling distribution of the mean and see the distribution is somewhat wider than when n was 100. Now, what is the likely error for this distribution? Well, first we need to find the standard error. The standard error is the population standard deviation, which is 100, divided by the square root of the sample size. Square root of 25 is 5. 100 divided by 5 is 20. The standard error of the mean is 20. And so then the likely error is about double that, around 40, actually 1.96 times 20. If we had an even smaller sample, let's say n of 5, kind of a silly small sample, we'll find that our sample observations again are spread across the range of the population. But the sample mean is again bounces around 500, sometimes above it, sometimes below it. We might look at the obtained sample means, and if we had done this 100 times, we would get a distribution which is quite spread out. The sampling distribution of the mean in this case is quite a bit wider than it was with n of 25. We could compare these sampling distributions of the mean easily. Here it is with n equal 5, here it is with n equal 25, and here we have with n equal to 100. So what have we learned from this? We began with an n of 1, and when n is 1, the standard deviation of individual scores is 100. The likely error, plus or minus from the mean, is 196. Sample of 5 gives us the standard error of 44.7, which is a likely error then of 87.6. That is 1.96 times the 44.7. When n is 25, the likely error is 39.2, and when n is 100, the likely error is only 19.6. What if we wanted to have a likely error of around 10 or less than 10? Well, that would mean cutting the error in half. There's a very nice rule of thumb. If you wish to cut the error in half, you need to quadruple the sample size. We can see that happening from going from 25 to 100. When we quadrupled the sample size, the error was cut in half. If we used a sample of size 400, the standard error of the mean would be 5. So here we see the trade-off between precision in our estimate and the size of the sample, and we have to make some considerations. Is it worth the extra effort to get the extra precision? Take-home message is the sampling distribution of the mean is the distribution of all possible sample means for samples of a given size. The problem is we never actually observe either the true population distribution of individual scores or, even less so, the distribution of possible means. We have only one mean that we've observed. However, we know from the central limit theorem what the distribution of means looks like relative to the population distribution. This sampling distribution of the mean allows us to compute likely error as an index of how accurate our sample mean is likely to be. And most importantly, here is this beautiful little formula showing the relationship between the standard deviation of means and the standard deviation in the population. I call this the 4-star formula. You don't need to memorize many formulas in statistics, but this is one that comes in handy to give you a good sense of what to expect when you draw samples. This sampling distribution applet was programmed by Michael Healy in the early days of WISE. Here's our WISE team as of May 2014. I hope you found this video useful. I invite you to visit our website at wise.cgu.edu for other resources in support of teaching and learning statistics. Thank you for your attention.